All right. Well, thank you everyone for being here this morning or evening for you. So I'm going to be talking about a new possible origin for PGE reefs and focusing on a case study of the J-M Reef. And this is work that I did during my PhD at Carleton. So the J-M Reef is a low sulfur platinum palladium deposit hosted in the Stillwater complex in southwestern Montana. It runs along strike for about 40 kilometers along the northern flank of the Beartooth Mountains. And it was discovered by Johns Manville exploration geologists in 1973. It's a world-class PG deposit with grades over 20 ppb or ppm palladium plus platinum over about a meter and a half. And the reef is hosted in coarse-grained to pegmatoidal olivine cumulates. So the goal of this project was to see if we could model both the origin of those olivine-bearing rocks and the high tenor sulfides in the reef. So these two columns are showing the stratigraphy of the Stillwater complex, and we're going to be focused down in the lower banded series down here. And in detail, the olivine-bearing zone is also called the troctolite anorthosite zone, and it can be broken down into three subzones. The gabbro subzone, which is made up of complexly interlayered norites, gabbronorites, and anorthosites, and that's overlain by the anorthosite subzone, where the reef is hosted in a package of rocks known as the reef package. And again, those are very coarse-grained textured rocks, which are overlain by more anorthosites and troctolites that tend to have finer grain textures. If we look at the stratigraphy at the mine scale, this is the Stillwater Mine area, and you can see that the J-M Reef unconformably overlies the footwall cumulates. So you have layers of the norite zone and gabbronorite zone 1 underlying the reef, and there's an angular unconformity with the olivine-bearing zone, which hosts the reef. This is the 5700 plan view map in the Stillwater Mine area shown here. And you can also see that sometimes the olivine-bearing rocks also undercut the gabbronorite layers, forming these things that the mine calls gabbro blocks. And you also see J-M Reef mineralization leaking down into the footwall, forming lenses and layers of disseminated mineralization in the footwall cumulates. So in order to build our thermodynamic model, we needed to collect data. So we could constrain our model using mineral chemistry and geochemistry as best we could. So the project started by collecting rock data from a very long drill hole that was collared down in the top of the ultramafic series in what's called the bronzitite zone. And it's drilled up through the norite 1 stratigraphy into gabbronorite 1, and then unfortunately hit the South Prairie Fault, which can run parallel to the J-M Reef. So our stratigraphy is truncated at that point, but you do see a spike in palladium platinum in the South Prairie Fault, presumably where it disrupted the reef. We also had a definition hole that was drilled in gabbronorite zone 1 up through olivine-bearing zone 1 in the J-M Reef and up into norite 2. You can see again that those footwall rocks near the reef tend to become complexly layered with gabbronorites, norites, and anorthosites kind of coming in and out. And sometimes they also host orthoperoxenite zeolites. If you look at the PGE chemistry in the footwall, you can see that it's moderately enriched in PGE with about 30 to 50 ppb palladium plus platinum in the footwall. So some other features of the reef, as we just showed, there's an unconformable relationship between the olivine-bearing zone and the footwall gabbronorites and norites. Footwall rocks are moderately enriched in PGE, and they do host disseminated sulfide, though it's not a lot. The sulfur isotopes indicate that there's little to no crustal input of external sulfur. in the J-M Reef. And the reef tenors are extremely high, but they are variable at both the local and the deposit scale. So from those constraints, we were able to build our melts model. So we started with 100 grams of a gabbronorite mush, so it's a feldspar, PX, CPX, and liquid mush at 1150 degrees in the 3 bar in the upper crust. Into that footwall gabbronorite mush, we titrate in 1 gram increments of the contaminated komatiite liquid that hosts 11 ppb palladium and is near its liquidus at 1315 degrees C. After the footwall mush and the contaminated komatiite react, any hybrid liquid that's produced in excess of 40% is removed or fractionated away from the system. And at each step in our model, we calculate the sulfur content at sulfide saturation using the model of Smythe. We also calculate the sulfide tenors at each step, and any sulfur or palladium that's dissolved in the silicate melt is fractionated away, and that's controlled by SCSS and also the concentration of palladium in the silicate melt. And we just simply calculate the palladium tenors using the flow system factor model of Gamble. These are the results of our melts model. So again, we're starting with a footwall gabbronorite that has a little bit of dissolved sulfide liquid, or sorry, it has a little bit of sulfide liquid hosted in it. And we begin to increase the temperature as we titrate in our contaminated komatiite. During that process, clinopyroxene is dissolved, feldspar is dissolved, and we're left with a harsbergitic restite up until we reach about 1250 degrees C. Sulfur or sulfide in the footwall actually increases, and it's being upgraded by the incoming undepleted melt. Once we hit 1250 degrees C, we begin to actually dissolve some portion of that sulfide liquid that's in the mush. Olivine continues to grow, and orthopyroxene begins to dissolve. If we look at what's going on with sulfur in the system, this curve in black is showing SCSS. You can see that over the duration of the model, SCS gradually increases very slightly, where there's a change in a phase disappearing from the system. And sulfur in the system goes up for a while, and then it begins to decrease. And so the x-axis is showing the amount of incoming liquid that we've titrated into or infiltrated through our footwall mush. We can add incoming melt until we get to about 800 grams of added liquid, at which point the entire system becomes sulfur undersaturated and all of our sulfide would be dissolved and all the metals would be released back into the silicate melt. If we look at what's going on with the palladium tenors, you can see that they are gradually increasing as we titrate in more and more liquid until they reach about 700 grams, at which point we've begun to match the measured tenors from the J-M Reef. The bulk palladium grades reach a little bit more than 1 ppm, which is still considerably less than what's found in the reef, where we have about 14 ppm palladium. But we can imagine that some of those sulfides are going to filter down and sort of form a narrow layer, which would be. So, in summary, this model is constrained by both thermodynamics and mass balance. And we can add about 800 grams of incoming melt to our 100 grams of footwall mush before the system becomes sulfur undersaturated. That initial 100 grams of footwall mush becomes 10 grams of olivine plus sulfide restite before the system becomes sulfide undersaturated. The tenors approach those or exceed those of the J-M Reef, and the modeled grades also begin to approach what the would be acceptable for J-M Reef grades. The instantaneous R factors of our model are typically in the 100s, and towards the end, when we begin to dissolve a considerable amount of sulfide liquid, they reach the thousands. But there's not this ridiculous amount of sulfide liquid compared to, or this minuscule amount of sulfide liquid compared to the silicate melt. It's always been difficult to sort of understand how you could equilibrate so much silicate melt in such a little volume of sulfide liquid. But the cumulative R factors do have very large values, between 60,000 to 2 million, which sort of approaches what's been predicted by R factor modeling for the J-M Reef R factors in 10 to the 5th to 10 to the 7th. So going back to the features of the reef, this model accounts for this unconformable relationship between the olivine-bearing rocks and the noids. Our olivine compositions are relatively iron-rich, with forsterite maxing out at about 85. We also can produce these unusual textures that people call mixed rock with olivine and pyroxene. We don't need any external sulfur. In this model, all of the sulfur comes from either the incoming melt or the finely disseminated sulfides in the footwall. And we were able to achieve those extremely high PGV tenors of the reef sulfides. And the variable character or heterogeneous distribution of the sulfides can be explained by differing amounts of infiltration at the mine scale. So in conclusion, we're dissolving footwall mush by introducing an incoming melt. We are upgrading footwall sulfides, and to some extent, those sulfides are being dissolved. And the volume of silicates is decreasing because of this dissolution process. And so in the future, we'd like to see if this sort of infiltration model can be applied to other reef type deposits, particularly where erosion of the